Chapter 14, Section 6 is about the pH of bases. And this is really exactly the same as what we learned yesterday about the pH of acids, except for if you're finding pH, there's going to be an extra step. For bases, our X will be hydroxide, and so then we'll have to convert that to hydronium concentration and then take the pH. So there's that one extra step. So first, strong bases. Strong bases would be the hydroxides of group 1A especially because they're soluble, and group 2A to a lesser extent because they're not very soluble, so only the part that dissolves is strong. Only the part that dissolves separates all the way into ions. For example, let's calculate the pH of a 5.0 times 10 to the negative second molar NaOH solution. So we ask ourselves, what's in the solution? Well, we have 5.0 times 10 to the negative second molar base, and it's a strong base, so it's going to separate totally into ions. So we have 5 times 10 to the negative second molar hydroxide from that, and we have 10 to the negative 7th molar hydroxide from my water. So clearly that one's not going to be very important, and so my main source is the sodium hydroxide. So I know that sodium hydroxide separates into, when it's dissolved in water, sodium ions and hydroxide ions. I can see that one of these makes one of these, so it's a 1-to-1 mole ratio. So I will have 5.0 times 10 to the negative second molar hydroxide. At this point, there's several ways to find the pH. We can use our hydroxide concentration to find H+, or we can find the POH and then find the pH. I'll show you both ways. So I know that I have the equation hydronium, or H+, times hydroxide is equal to 10 to the negative 14th. So I know that H+ is equal to 10 to the negative 14th divided by hydroxide. Then I find out that H+ is 2 times 10 to the negative 13th. And then I can take the negative log of that to find the pH. And I find out that the pH is 12.7, which makes sense because it's a base, so the pH should be greater than 7. Another way you could have done that is you could have, once you found the hydroxide, you could have said, well, POH is equal to negative log of the hydroxide. And so that would give you a POH of 1.30, and then you would use the equation that pH plus POH is equal to 14. So 14 minus POH is equal to pH, and you would get 12.7. Now let's take a look at some weak bases. For example, ammonia. Go ahead and pause the video and write down how ammonia reacts with water. It's a base, so how does it make hydroxide with water? Finish the equation. So you should have said that this base takes a proton off the water, takes an H off the water, so you wind up with NH4 plus and hydroxide. So there's how a base can make hydroxide even if it doesn't contain any hydroxide in the formula. And this is a weak base, so it's not going to do that all the way. In fact, it's going to do that a very small amount. This has a Kb value, so it has an equilibrium constant. Because it's weak, it doesn't separate all the way and it reaches equilibrium. So go ahead and write your equilibrium expression for ammonia, which is called K with little b because it's a base. So you should have the concentrations of the products on top and the reactant on the bottom, and water should not appear in it because it's a pure liquid. So only include aqueous and gas, not solid and liquid. Now let's do an example of finding pH for a weak base. For example, calculate the pH for a 15.0 molar solution of NH3 NH3 has an equilibrium constant Kb equal to 1.8 times 10 to the negative fifth. On a side note, notice that this equilibrium constant is the same as the Ka for acetic acid. That actually shows up in the multiple choice of AP tests sometimes. So apparently they want you to know that value, which I think is kind of silly. But if you want those points, then you'll learn that value. So I need to have my equation. And I ask myself, what am I trying to solve for in this problem? And it's the hydroxide, because hydroxide is related to H+, which is related to pH. So as always, I'll make my ice table, and I'll set it up, and I'll solve it. So I know that initially I have 15.0 molar ammonia. Water doesn't matter because it's not in my equilibrium expression. It does not appear in the equilibrium expression, the math equation for calculating K. And these are 0. I'm going to use up some of this and make some of these. And so overall my equilibrium is 15 minus x, x, and x. So what I want is hydroxide concentration, which is x. So go ahead and pause the video, solve for x, and find pH. So here is your equation that you need to solve. So on your calculator you can graph y equals 1.8 times 10 to the negative fifth and y equals x squared over 15 minus x. The intersection should be at 1.6 times 10 to the negative second. That's equal to hydroxide ion concentration. So then you can solve one of the two ways we did earlier, and you'll find that the pH is equal to 12.2. Let's do one more example. This one we'll go backwards in. The pH of an ammonia solution is given to us. It is 11.00. What is the concentration of the solution? So we're trying to find the initial concentration, the one everybody talks about. You say you have, 1 molar ammonia or something like that. Really, you don't have 1 molar ammonia because part of it has separated into ions to reach equilibrium. But you just say, what is the concentration of the solution? That means initial concentration, pretending it's all together. So we're going to use the ice table again. Go ahead and set up your ice table for ammonia and figure out what you can get from your pH. See if you can do the problem. So here's how my ice table looks. It's the same as before, except for I don't know the concentration of NH3. That's what I'm trying to find. Luckily, we do know X. X is equal to the hydroxide concentration. So if you weren't sure what to do, you haven't already done it, go ahead and solve for the hydroxide concentration, which is your X. So there's two ways you can do it again, but I'll say pH plus POH equals 14 and use that equation to find my POH is 3. And then I know that my hydroxide ion concentration is 10 to the negative POH. It's just the inverse of my POH equation. POH is negative log of hydroxide, so hydroxide is 10 to the negative POH. So I know that that is equal to 10 to the negative third molar. And that is my X value. So now I'm going to go ahead and plug everything into my equilibrium expression and solve for I, my initial concentration. So I get that K is equal to x squared over I minus x. I'll go ahead and graph that. Y equals 1.8 times 10 to the negative fifth, and y equals 1 times 10 to the negative third squared over x minus 1 times 10 to the negative third, and find the intersection, and that'll be my I value. Then I found the intersection of 0.057 molar for my initial concentration. Last for today, let's mention that there is a relationship between Ka and Kb. So if you ever are given one of them, like in a table or something, but you really need the other one, so like if you have a table of Ka for NH4+, but what you need is a Kb for NH3, its conjugate base, then you can use this equation to get the one you want. Ka times Kb is equal to Kw. Here's the work I was talking about. If you add up the equation for Kb with the equation for Ka, then the NH4+ cancel out, the NH3's cancel out. So what you're left with is the equation for the autoionization of water. And this one, of course, forms equilibrium with the equilibrium constant called Kw, where you get 10 to the negative 7th molar hydronium and 10 to the negative 7th molar hydroxide. So if you add up these two equations to get a third equation, if you want the K value, you multiply the equilibrium constants. Chapter 14, Section 7 is about the pH of polyprotic acids. Those are acids that have more than one hydrogen on them that they can lose. For example, H3PO4 actually has 3 hydrogens on it, 3 acidic hydrogens that it can lose. So there's the first hydrogen that can come off. That would be the H3PO4 reacting with water, and then one of the hydrogens comes off, and so it would make H3O+, and you would be left with H2PO4-. That one is a weak acid, so it would set up the equilibrium. The equilibrium constant for that one is called Ka, because the acid, Ka1, because the first hydrogen coming off. Go ahead and pause the video and write the chemical equations for the second hydrogen and the third hydrogen coming off. So the second hydrogen coming off would have a Ka value Ka2, and the third one coming off would have your equilibrium constant called Ka3. On a side note, like I mentioned last time, if you wanted the overall K for all three, you would need to multiply the individual K values, because you would be adding all of these together. And so it would mean you would have all those products on the top of your equilibrium expression multiplied by each other, all those reactants on the bottom multiplied by each other. So if you wanted the overall K value, you would multiply the Ks. Let's find the pH of a polyprotic acid. For example, calculate the pH of 5.0 molar phosphoric acid. Ka1 is 7.5 times 10 to the negative third, Ka2 is 6.2 times 10 to the negative eighth, and Ka3 is 4.8 times 10 to the negative 13th. Now, it seems like you would have to do all of those and find the overall concentration, but it turns out it's a lot easier than that, because look how much bigger your Ka1 is than the other two. So it turns out that this one matters. These are so much smaller that what it means is that the first proton, the first hydrogen, pretty much comes off enough to matter. The second two mostly stay on as H2PO4-. So we can just use Ka1. So you would just do an ice table with Ka1. You would wind up with 7.5 times 10 to the negative third is equal to x squared 5.0 minus x. Solve for x. When you solve for x, you wind up with 1.9 times 10 to the negative first. That is equal to your H plus concentration. Then you take the negative log of that to get your pH, and pH in this problem is equal to 0.72. So if you need more practice with that, you can try it, but the new thing is that even with all those Ka values, only the first one is important. And that's true for all the polyprotic acids except for sulfuric acid. For sulfuric acid, if the concentration is less than 1 molar, the second Ka value is actually enough that we must add it in also. For example, calculate the pH of a 1.00 times 10 to the negative second molar sulfuric acid solution, where Ka2 is 1.2 times 10 to the negative second. So that's actually a fairly big K value. You might wonder what happened to Ka1. Well, sulfuric acid is a strong acid, so Ka1 for the first proton coming off, first hydrogen coming off of H2SO4 is just large. Go ahead and write your chemical reaction for what Ka1 would be based on, the first hydrogen coming off. Pause the video and do that one, and then the second one. So here are your reactions. The first hydrogen comes off in step 1. It comes off pretty much all the way because H2SO4 is a strong acid, and then it's almost completely turned into HSO4 minus. Of that, a bunch of that hydrogen comes off also, enough to be significant in pH calculations. So you need to add this in using an ice table to the initial amount also. So let's go ahead and calculate our H plus concentration from both sources. So from source 1, I'm starting off with 1 times 10 to the negative second molar H2SO4. So that will give me 1 times 10 to the negative second molar hydronium from this first step. And it will also give me 1 times 10 to the negative second molar HSO4 minus, which is going to fall apart further into H plus in step 2. So for step 2, we need to make an ice table. We have our concentrations. We calculated our initial concentration of HSO4 minus to be 1.00 times 10 to the negative second molar. H2O doesn't go in our ice table. Hydronium does have an initial concentration because we already have a bunch of that in there from the first step, so that's a little bit different than what we've done before. So we have initial concentration of hydronium from the first step, and sulfate is 0. So go ahead and pause the video and calculate the equilibrium concentration of H3O plus from the second step, and then add it to the first step and find the pH. So here's how your ice table should turn out. So when you set Ka2 equal to products over reactants, you find out that X is 4.5 times 10 to the negative third. So your total hydronium concentration is this one. So the total is 0.0145 molar hydronium. That's the first dissociation plus the second dissociation. When you take the negative log of it, you find your pH is 1.84.